I'll leave this down here for now. All right, so if this is our array, this would have ultimately created for us let's do it this way. A variable named AR. And this variable named AR is said to point to the value in memory. Now let me show this to you initially. So we're going to go back into our code for a second. And I'll go ahead and create an int array named AR is equal to a new int array 5. And let's see what were my values in here. I actually have 6. 5, 7, 14, 218. Oops. 5, 7, 14, 218. Okay, so I built my array AR capable of holding 6 integers. So just like we did on Keynote. Then I went ahead and I filled it up with all my values. Then I'm going to say system.out.println AR. When I run this, you're going to see that what prints out, even though AR is filled up with 5, 7, 14, 2, 1, 8, filled up with a bunch of numbers, what prints out is a crazy memory address looking thing. Okay? You'll actually recognize this as a hexadecimal number. Also connected with what we talked about. So 3DFECA64. So giant number and hexadecimal. But in any case, this is a memory address. Okay? I don't remember, maybe the first or second day of class that I mentioned something about the reason I don't use a textbook is the textbooks lie to you and say that pointers don't exist, blah, blah, blah. Okay, well, pointers are primitive type variables for holding memory addresses. There's a memory address. There's a variable that holds a memory address. That's a pointer. They exist in Java. So when a book says it doesn't exist, they are lying to you. Clearly, the author was just doing it for the money and didn't understand Java. So in any case, when we print out that memory address and we print out that variable AR, we get the memory address where it lives. Let's talk about why. So AR is the name of my variable. Variables hold values. The type of value that AR holds is a value of type integer array. And an integer array dictates how arrays work. And I'm going to show you that through example here. So just to keep our math easy, let's just say that AR has a value of 100 rather than the crazy memory address we just saw. Okay? We lucked out and got a nice, friendly looking memory address. Okay? Okay, now remember, arrays need to be contiguous in memory. So every bucket of our array sits right next to the previous bucket in memory. So I went ahead and put the very first bucket at memory address 100, the second one at 104, 108, 112, 116, 120. Why is the second one at bucket 104? Why is it at memory address 104 instead of memory address 101? What type of value is it? An int. Ints are 32 bits, or as you said, 4 bytes. So, let me do this a couple different ways here. So AR at bucket 0 is the same thing as saying, go to AR, add to that 0 times the size of int. Size of int, as you pointed out, is 4, correct? So let's do this on the second line here. Which is actually equal to AR, which is 100. That's the value of AR. It's 100 plus 0, which is 100. So bucket 0 of AR is at memory address 100. What if I wanted AR at bucket 3? AR at bucket 3 is AR plus 3 times size of int, or AR plus 3 times 4, or 100 plus 12, or 112. Which is where bucket 3 lives. Put another row of, here I'll actually put the memory addresses above, and then I'll put the indexes below.
Wait, so does that mean, or not, where it says size of int, like does the of have to be capitalized?
This isn't real syntax.
Oh.
This is, I'm just saying whatever the size of an integer is. So integers are 32-bit signed numbers, or 4 bytes, because a byte is 8 bits. Okay, so here's our full array sandwich. Arrays have bucket 0, bucket 1, bucket 2, bucket 3, bucket 4, bucket 5 in this case, because it's a 6-bucket array. Then we have the values in each of those buckets, and then each of those buckets also live at a specific memory address. Okay? And the proof of the contiguousness of memory is that to walk through an array, I think I mentioned before break that arrays are fast from a performance perspective because bucket location can be calculated mathematically. That is, if I want to get to bucket 3, I go to the base address of AR, which is 100, so I zip up into memory and then go to 3 times the size of the kind of value being sent and just jump to the value. I don't have to walk 1 bucket at a time. I could just go to the memory address where it lives. Okay? So arrays are very fast from that perspective. All right, so let's talk about some of the pieces here. So do we understand how arrays work in general? Okay? From our perspective, we don't necessarily care if they're stored contiguously or not, but under the hood, this is interesting stuff. Especially helps you on the next class where you appreciate things that are memory inefficient, but performance versus memory efficient and lower performance. Those tend to be trade-offs throughout technology. So we've been introduced to a new keyword called the new keyword. We saw it in use right here. So we said int array AR is equal to a new int 6. So whatever value we put in here, that's how many buckets we're creating. Whatever this guy says must match whatever this guy says, and that's the type of value that we're storing. The square bracket says that we're making an array. All right, and this is just our variable name. But now, if you think about the generic syntax for variables, variables are type followed by var name equals value. Correct? All right. So here's my type, integer array. My variable name is AR. My value is whatever this guy boils down to. And what was that value? Creepy memory address, i.e. the non-existent pointer. All right, so where did that come from? We have this new keyword. I refer to the new keyword as our real estate agent. You probably will not find this in any of the Java books. In real life, what's a real estate agent do? Okay. And when they find you a house, do they show up at your office or your house and they bring you the house? No, they tell you where you can go find the house, or more than likely, they come pick you up in their minivan. They always drive minivans. What's up with that? Have any of you experienced that? Really? Man, like the last 6 real estate agents I've worked with have all minivans. Well, no, I can understand just why a minivan. Well, actually, probably minivans are probably a lot less expensive than like SUVs, even though they basically serve the same purpose. You know, because like all these people own SUVs, but it's like not like they go off-roading. It's like, well, I did go off-roading. There's some potholes on 43 when you get south of Mech 1. That's off-roading. So in any case, the new keyword is our real estate agent in our computer. We are asking them to go find us a plot of land big enough to hold, in this case, well, here, let me just go back to this many of these guys. So an int is 32 bits, or 4 bytes, and we need 6 of those, right? So that's 24 bytes. We need a plot of land that is 24 bytes big, and we need it to be all next to each other, okay? So that new keyword is going to go and talk to the operating system and say, hey, we need to go find some memory for this person who's shopping around. We need to give them the address where they can go and find their lot for their land. Okay? That's what the new keyword does. So a real estate agent always returns a memory address. Oh, well, then I guess it would flip out and throw an exception. So that's possible. So it'll always try to return a memory address. It will, when successful, it will always return a memory address. I suppose if there's not enough memory left over, then it actually becomes more interesting in Java. Since Java is a virtual machine, when you launch Java, and I can kind of show you this. So if I go in, I run the help utility for Java. Let's see, one of the things we can do. I need to do dash. I thought one of the things I could do is change the amount of memory. Oh, print help on non-standard options. Okay. So just dash X.
Size, heap size.
Yep, stack size, heap size, so we can choose how much memory to associate with our Java virtual machine. So your virtual machine is like a software application that runs on top of the operating system. It's actually there. So you can run out of memory in the Java virtual machine and not really have any issue in the rest of the real world of your computer. Every Java program runs in its own virtual machine. So what becomes interesting about that is if we wrote a program that, we were talking about this before with running out of memory if you have an infinite loop.
Yeah.
We just kept adding something, adding more memory, more memory, more memory. Java would eventually scream at you and say, hey, we've run out of stack size. Did we talk about recursion at all last time? Briefly mentioned method that calls itself. Did we talk about factorial or anything?
Yeah.
Did we write the code for it?
Yeah.
Okay, so did I show you an exception like stack out of space? So just real quick, it only takes a second just to show you what happens when memory breaks. So if we're writing the factorial problem, factorial, like 4 factorial is actually 4 times 3 factorial. 3 factorial is actually 3 times 2 factorial. So it's a recursive implementation. So we'll ask the question, if n is equal to 1, return n. Otherwise, return n times driver dot factorial of n minus 1. You sure I didn't show you this thing breaking? Did we write this last time?
No, we didn't write it last time. We did factorial like 2 times ago. We didn't break it.
It was from lesson 3.
Okay.
And you didn't break it. You showed us a little bit of stuff.
Okay. Well, in any case, so this will run fine. Driver dot factorial. I'll pass it a 4, and we'll print that out. And we'll get our 24. Now, factorial is actually a being a recursive function. It's very memory inefficient. It's a nice, elegant solution, but it's very memory inefficient.
You have to put stuff on the stack.
Yep, puts the entire copy of the method on the stack to put it on hold until it can finally get the next answer. Well, if we make one little mistake in here, like forget to subtract 1 from n, we're going to say, oh, factorial 4 is actually 4 times the factorial 4. Factorial 4 is actually 4 times the factorial 4. 4 times the factorial 4. 4 times the factorial 4, until it screams at us. And this is what it'll do. So it gives us an error that says java.lang stack overflow exception, or stack overflow error, and it's an exception. That's what this guy is. So that's telling us that you ran out of stack space in Java. The Java virtual machine, we ran out of stack space. Now, if I were to adjust the virtual machine to give us more stack space, it would take longer before it crashed, but it would still crash. So this is showing us how many times it had to call factorial before it died.
Wow.
I'm assuming the 20 and the 24 have to do with your line, which line
Correct.
information is on, but
Yep.
why does it give you 20 and 24 and not, or, okay, I understand why it gives you 24, but why is it giving you 20 originally?
Well, 20 is, that's actually a good question. Maybe it's just right at the beginning of factorial, and that's where it finally ran out of memory. Because it was only 20 the very last time.
Or I think it's the very first time.
That was the first time.
Well, this thing's a stack trace, so I think it's the very last time. So this would have been the very first call, and then it unravels. So when you go all the way up here to the top, it goes all the way. It would actually be the very first call, so it must be when it came back into the first call of the method that takes us to line 20. But it's the very last thing that happened, was it errored out there. I don't know why line 20. I'm guessing this is just when it removed the method from the stack to try to unpack it and said, this is where I've died. But it would have never actually gotten to this point. Oh, I do know why. It was the very last thing. As soon as it tried to resolve n, it realized it was out of memory. It couldn't resolve this variable, so it actually died on this line when it recognized, I'm out of memory. I can't get this value. There's nowhere to get it from. Memory's full. Okay, well, so anyways, that's how memory kind of works in Java, but really on any system. Older languages like C and C++, if you were to write an infinite loop like that, it could potentially crash the computer.
That's reassuring.
Yeah, I mean, because you were literally working in real memory. That's one of the problems that Java attempted to fix. Okay, so new keyword. Real estate agent always returns a memory address, which means that any variable on the left side of the assignment operator where the new keyword is on the right side of that same assignment operator is a pointer. If the new keyword's on the right side of the assignment operator and you have a variable name on the left, that variable is receiving the value returned by the new keyword, which is a memory address. That's a pointer. A variable that stores a memory address is a pointer. Okay. So that's our new keyword. That's what it does for us. It asks the operating system for some memory. It brings back enough memory, it brings back the location where there is enough memory in a row to store this many of these guys. Make sense? Okay, so now let's start experimenting a little bit with arrays. So I filled up this array with some values. Now I want to write a loop that loops through all the elements in my array. So there's my 6 values for my array. So I built the array right here. I filled it up, these lines right here, and then I looped through it. Notice that our loop is very, 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 very similar to the loop for strings, for looping through every element in a string. With one exception. Can anybody spot the exception? Go ahead.
Put the parentheses after length.
No parentheses after length. Was that an error? Huh? Program seemed to run. Probably not an error. What does it mean if there's parentheses? So when we say, if we are dealing with a string s, and we say s.length, what is length? Well, that's the parameter list, so length is a method. Okay, so length is actually a method. And we know it's a method because it has the opening and closing parentheses, which is the parameter list. It's an empty parameter list, but a parameter list nonetheless. In this case, length does not have a parameter list, which means it must not be a method.
Instance thing?
It is an instance. It's an instance field. Okay. Now, this is important. Got to go back from the beginning. There are 2 types of methods: instance methods and class methods, right? Instance methods, we know they're instance methods if they were defined without using the keyword static, or if they are called using an instance of a class. That means it's an instance method. Class methods are defined using the keyword static and are called using the class name associated with the method. Class name in which the method was defined. Okay? Those are for methods. Now, where do methods fit in the big scheme of things? What's up?
Not very major.
Methods live inside of objects. We're going to start writing our first object next class, but just as a precursor to that, objects are collections of constructors, which we don't know what those are yet, methods, and fields. Forget about constructors right now. We know what methods are. Fields are variables associated with an object. So fields, a field is a synonym for a variable. And fields come in both class fields and instance fields, just like methods do. So really the rules that we've learned that revolve around instance methods and class methods are the identical rules for instance fields versus class fields. An instance field is defined without using the keyword static. Class field is defined using the keyword static. How do we know it by seeing it being called? If a variable, if a field is being called using the name of the class, it must be a class field. If it's being called using an instance of a class, it must be an instance field. Is this guy the name of a class or the name of an instance of a class? It's an instance. It's a variable name, not the name of a class. Therefore, it's an instance. So this guy is calling his length method. But it's not a method. It's a field. So arrays have a field that just holds the value, which knows how many elements are in an array. So it's not calculating it, it just holds it. And I've already told you that strings actually just hold a value as well. Because hint, hint, strings are actually implemented under the hood as character arrays. So if you were to look under the hood of the string class, you would see right at the top, one of its main fields is a character array that it uses to store its actual crap. So what's the length of a string? It's the length of that character array. That make sense? All right, so not really a huge deal. This is really something you just have to remember, that arrays, the length of an array is actually a field, where the length of a string is a method. And I'll be able to talk a little bit more about that once we introduce objects as to why they made that decision. Kind of the short version of the answer is arrays are very, very, very old, much older than objects. So we have a lot of leftover syntax. Remember, Java is a C-based language. So it came from C++, which came from C. So a lot of the syntax that lived back then has come through to today, rather than making changes because they wanted people who already knew those older languages to be able to immediately start writing software in these newer languages. Now, an interesting thing about... I want to talk about it. Well, let me show it to you this way. When we looked at not good enough. Okay, when we looked at these, was this in this class? Different class. Okay, well, we'll pretend like it was in this class because you're seeing some stuff that I already wrote in the slides, right? Size of crap, stuff like that. So up here we have an array. So this is our main method in a language called C. This is C syntax. So all programs begin and end with main. All programs begin and end with main. So if we look at our Java program, our main method takes in a single parameter string array named args. In C, our main method actually took in two parameters, int argc, and this is a string array called argv. It's actually a char pointer, which is a pointer is an array. We've already seen arrays are pointers. Not all pointers are arrays, but all arrays are pointers. Relatively unimportant in this example. A char pointer is an array of strings. Okay, so this is just old-time syntax for saying this. String array. Okay, this is when we used to deal with pointers all the time. This is why it's a common belief that pointers don't exist in Java, because they've taken the special syntax out for dealing with pointers. So you use pointers without actually knowing you're working with them in Java, which is why they say that pointers don't exist. So I highly doubt a lot of the people who are writing these books actually believe that pointers don't exist. They're probably just sugarcoating it because they think that their audience is too stupid to know the difference, I guess. I think it's pretty important we understand what's going on under the hood so that we can figure things out in the future when we run into weird bugs. In any case, there are two parameters here as opposed to one parameter that we have back here. Why is that? It's because in older languages like C, a string array, any kind of array for that matter, did not know how many elements was in it. So you had to pass along the argument count. Arrays did not, historically arrays did not know how many elements were inside them. So you had to keep track of that. As you added crap onto the array, you had to keep track of how many things were in there. So, for instance, the new keyword today is something we take for granted, but we used to have to allocate memory. So back in early C, we might create a int pointer called AR, and this guy might be Malik 6 times size of int. So what we just did is we asked for enough memory, and this is memory allocate, enough memory to hold 6 times whatever the size of an int is in this particular language. Okay, so this would get me 24 bytes. This would return a memory address where there's 24 bytes stored inside of AR. If I were to print out AR, you'd see a weird memory address. And then if I wanted to say AR at bucket 0 equals 5, I could do that, or I could say let's do it this way. AR concatenated with, AR plus 2 times size of int star is equal to 8. That will put in bucket 2 an 8. Because rather than using the simple syntax for saying just take me to bucket 0 or take me to bucket 2, I'm saying travel to this memory address. Once there, by putting a little star after it, you're saying I'm setting a value. Set the value at that memory address to this guy. Okay? So we used to have to manipulate memory directly. Now we don't have to do that. Now we get to just say AR at bucket 0, 1, 2, 3, whatever, everything's fine. We don't have to deal with any of this memory allocation crap. It all just works. Okay, but this stuff used to exist. Still exists, actually. But we do have an upgraded version of arrays in Java that we did not have in C++ or C, and that is an array that is aware of how many characters are inside of it. That came from arrays being, let's say, upgraded to a higher class citizen in Java, where they're actually implemented in terms of objects rather than as primitive types as they were in the older languages. So I mentioned a little bit ago, arrays are only kind of half objects in Java. They're implemented as objects, but they act like primitive types. So we still would like to think about them as primitive types, but they are in fact objects, and one of the perks of that is arrays are able to keep track of how many elements are in them. So now if we're going to pass arrays to our methods, we only need to pass around the array rather than the array and how many things are in it. Make sense? The same can be true in old style strings. If I wanted to create a string in old C, I would create a char pointer. If I wanted to have 10 elements in it, char pointer S is equal to malloc 10 times size of char. But I haven't put anything in it yet. All I have is a big empty bucket of space that I can start putting stuff in. Well, just because I created a footprint big enough to hold a 10 character char doesn't mean I'm going to put 10 characters in there, right? I need to know where the end of that char is. So in a language like C, the string termination character was \0. It's a special character that said end of line, string termination. So as you were walking through memory, you knew you reached the end of the string when you hit a \0. Does that make sense? Life used to be harder for programmers, if you can imagine. Okay, so Arrays today know how many characters are in them, but they get that, they deliver that number through a field, not a method. Besides that, the problem solving between arrays and strings in terms of loops is identical. Just don't put the parentheses on there for arrays, but it's because it's a field and not a method. Got it? Okay, so this will go through and it'll print out every element in my array. If I want to this would be a good time for this. Trying to decide what I want to. So I'm going to create a method called replace first element. This guy's we're going to go back to dealing with strings for a second because we want to compare strings and arrays quite a bit. So this guy's going to be called replace first element, where whatever the current string is, I want to replace whatever its first element is with this new first element, which is C, a new char. Okay? So I'm going to go ahead and I'm going to say string answer is equal to the empty string concatenated with C, my new char. All right? Because we're going to have to build a new string. We can't just change the string directly. One of the things with strings, right? Now we're going to create a loop. This loop's going to start at the second character. So I is equal to 1. I is less than s dot, I'm sorry. We need to actually pass in a string here. So we're going to pass in a string and we're going to pass in the char that we want to replace the first character with. I is less than s dot length, I plus plus. Each time through we'll say answer is equal to answer concatenated with s dot char at I. And in the end we'll return answer. All right, so what does this code do? It takes a string as a parameter as well as the new first character we want there to be. And it builds us a brand new string with our new first character and everything that came after the old first character in our string and returns it. Okay, now if we test this, I'm going to create a string s hello. We'll do a system.out.println s. Then we'll say we'll say s is equal to driver dot replace first element of s with a j for jello. Then we do system.out.println s. We'll see hello, and then we'll see jello.
You put back.
Okay. Similarly, we're going to build a char array. Now, before we do that, though, we need to give ourselves the ability to print char arrays. Arrays we can print directly. Or, I'm sorry, strings we can print directly. Char arrays we actually can, but we're going to pretend like you didn't hear that. So as far as you know, you can't print arrays directly. So we're going to create a static method called void, of type void, called print array that takes a char array as a parameter. And this guy will create a for loop for int I is equal to 0. I is less than ar.length. I plus plus system.out.print ar at bucket I. And then at the very end, we'll do system.out.println, empty string. That'll kick it down the line. Okay, so this is basically the exact same code we had when we printed out every element of a string, 1 character per line, except we did a print here instead of a println. So we're just printing out the character array 1 character at a time, and then pressing return here at the very end with the println. So I'm going to go ahead and I'm going to create my char array that's equivalent to hello. So I'll say char array AR is equal to a new char array 5. AR bucket 0 is equal to H, the character H. AR bucket 1 is equal to E.
Can you make like a char array named AR and an int array named AR?
You can't have 2 variables named AR. Doesn't matter what they hold.
Okay.
Yeah, you cannot have 2 variables within the same scope named AR. Just like I couldn't say string S is equal to elephant, because I already have a variable named elephant, or I already have a variable named S, rather.
Okay.
So just like phone numbers, variables have to be unique within their scope. All right, I'm going to go ahead and comment out my 2 print statements up here just so they don't muck up my output. And then I'll test my print array real quick. I'll say driver.printArray, and I'll pass it AR. And this guy should print out hello to the screen, proving that we've built an array, filled an array, and now we can display an array. Okay. Now, we're going to write a method, static.
Wait, can you print it one more time just so I can see? Sorry.
You want just to run it again?
Yeah, I just want to see. When printed that. No. Print array. I don't know what it's wrong. Oh, there it is. Gotcha.
All right, so I'm going to write another method down here, static char array, replace first element. This guy's going to take in a char array, name AR, and a char C as a parameter. Now I have 2 methods here with the exact same name. What's it called when I have 2 methods with the exact same name that it has a different number and or type of parameters? Polymorphism. So here's an example of polymorphism where I'm writing 2 methods with the same name. One of them takes a string as a parameter and a char. The other one takes a char array and a char as a parameter. Okay, and what am I doing to this second one? I am going to replace the very first character with whatever's in C. AR bucket 0 equals C. Return AR. Done. So right off the bat, we see the advantages of arrays from a changing them perspective. I didn't have to loop through. I didn't have to build a brand new string. All I did was say, hey, you want C to be the new first character? No problem. Done. And you know what? It gets even better. I'm going to show you that here in a second. Good?
Yeah.
All right. So we're going to go ahead and test that out real quick. So we're going to print our array AR. Then we're going to say driver dot replace first element of AR with J. And we'll store the result back in AR. Then we'll say driver dot print array AR. So we should see hello, then we should see Jello. Hello and Jello. No problem? All right. Now, I'm going to make a small little change to my version of replace first element here. Actually, before I do that, I'm going to make a change to this replace first element, the one that dealt with strings. Okay? So this one's going to build a brand new string. It's then going to update that new string. And instead of returning answer at the end, I'm going to set S equal to answer. So the string that was passed in, I'm going to set equal to whatever my new one is, hopefully overwriting it. Okay? Come back up here. S is equal to hello, print it out. It's going to print out hello. Then I'm going to just call driver.replace first elements, passing it S and passing it a J. And what do I hope that guy does? I hope it comes in here, builds a brand new string called answer, fills it up with all the right crap, and then in the end sets S equal to whatever answer is. And then I'm going to try printing out S again and seeing if it's now Jello. But this guy will print out hello twice. Hello, hello. The next one was hello, Jello from our array one. So there's our hello, hello. Okay, well that didn't work out the way we thought it was going to work out, but wait a minute. Let's go and do this for our array. We're going to have our replace first element not return anything. And I'm not even going to set AR equal to AR because I didn't build anything new. Comment out these lines up here. So I built my array, filled up my array, printed my array. It's going to print out hello. Then I just magically passed my array into this method along with a J. What does this method do? It just sets bucket 0 of AR equal to whatever that J was, whatever that variable is. Then I'm going to print it out again here. And what's it going to print out? It's going to print out Jello. But I never actually returned a value here. I never actually set AR equal to this new change to it. I just changed it directly. I just proved again that pointers exist. Because what did I do? To prove the point here real quick, I'm going to print out a line right here. I'm going to say system.out.println AR. And we've seen this before. This prints out a memory address, right? When we print out an array directly using println, it prints out a memory address. So I'm going to print out that memory address. And I'm going to do the exact same thing inside my method. Okay? So here's my method, replace first element, and I'm passing a char array into, as well as a primitive type. I'm going to print out whatever AR is. It'll give me a memory address. And what we're going to see is they are both the same memory address. Oh, 1 second. I actually need to use int arrays. Remember a few minutes ago when I said char arrays can actually be printed out directly? I said pretend like you didn't hear that. Well, now you actually just saw it too. Just for this example real quick. Int array AR2 equals new int array 5. I'm not even going to fill it with anything. I'm just going to say system.out.println AR2 because it exists even if there's not anything in the buckets. And I'll create a quick little method called blah that takes an int array as a parameter. And this guy will just print out that int array. Okay, so I created a brand new integer array called AR2 using the new keywords. That's going to return a memory address, right? Then I printed out AR2. So this is going to print out crazy memory address. Then I called this new method called blah that I wrote, passing it AR2. What does blah do? It takes in an integer array and prints out the memory address. And what we'll see is those two memory addresses are identical. I couldn't do this with char arrays because char arrays automatically get mapped to strings behind the scenes. They're kind of a special case. Pretend like you didn't hear. I just know it's a truth right now. I'll be able to explain that more when we have objects available to us. Okay, but the punchline here is two ways to pass variables to methods. Pass by value, pass by address. We didn't talk about this yet, did we? This is new. All right. This is actually one of the reasons why Java exists. I may or may not have used this example before, but I used something pretty similar to it earlier today in here. If you were having a party at your house tonight and you were inviting me to your party, you wouldn't hand me your house and tell me to open the door at 8, especially since it's already 9. Instead, you'd give me a piece of paper that had the address to where your house was, right? Okay. So you are not giving me your house. You're not passing your house by value. You are passing your house by address. You're handing me the address where I can go and find your house. Why? Because houses are heavy. That's why, correct? All right. In older languages like C and C++, the programmer was empowered to make bad decisions like that. As a C++ programmer, you could choose to pass the house as opposed to the address to the house. In C++, star, the syntax, we saw that, we saw that star syntax. Back out here. Little star thing. This says value. So star, let's do it back in here. In C++, star means value. Ampersand means address. So there's a syntax in C and C++ that allow us to dictate relative to a pointer whether we are talking about the value at the address the pointer points to or whether we are talking about the address itself. That make sense? So older languages like C and C++ empowered us to make those decisions. Which sounds all fine and dandy on paper until you're a beginning programmer and you start overwriting half your operating system because you haven't quite gotten the difference between star and ampersand down yet. Okay, so, or you're walking off the end of your arrays and that kind of stuff. So while C and C++ were very powerful languages, and once you got the hang of things, it wasn't that big of a deal, they did empower the programmer to make decisions that a programmer should never make. In real life, should you ever hand somebody your house? Never. It never makes sense to hand somebody your house. It always makes more sense to give them the address to your house, correct? Now, in real life, does it make sense to hand somebody a quarter, or does it make more sense to go and tell them where they can find the quarter? At the very least, it's a lot closer, right? Okay, so handing them the quarter probably makes sense. We can all lift the quarter. If you don't like them and you hid the quarter in a good spot, maybe you want to mess with them and have them go find the quarter, okay? But which is the bigger waste? If you make them go find the quarter versus hand them the quarter, it's a little bit inefficient on one of the sides, right? But if you hand them the house as opposed to a piece of paper with the address of the house, that's very inefficient. So those older languages allowed programmers to make decisions that they should have been capable of making. Because in real life, all of us would say, oh yeah, here's the address where I live. Nobody would say, oh, you're not just going to give me the house, you have to drive there. You know, nobody's going to say that, right? Okay, because we're not idiots. And it's just, we've figured that out. Well, beginning programmers haven't necessarily figured that out. If they understood what they were doing, they would say, oh yeah, I definitely don't want to give you the house. I'd rather give you the address to the house, but I haven't got my ampersands and asterisks in order yet, so I'm not exactly sure what I'm doing here. It seemed to work. And that's part of what you deal with when you're a beginning programmer. Sometimes you'll get code that happens to work, but you're not necessarily sure why it works. So sometimes in C or C++, you'd have a program that functioned correctly, but was horrifically memory inefficient because of how you were passing things around. One of the goals of Java, in the early days, Java was called C++++. That was like the joke behind the scenes. Java took all the things that were, well, in their opinion, took all the things that was good about the C++ programming language and fixed some things that were wrong about the C++ language. For starters, they decided we no longer empower the programmer to decide whether something is passed by value or by address. Sometimes passed by address is also called passed by reference. It's a synonym for it. Passed by address or passed by reference. Passed by value means we're actually giving you the real object. Here's the quarter, here's the int, here's the char, here's the house. Okay? Passing it by value is giving it the real object. Passing it by address is always giving you the 32-bit, or if you're on a 64-bit operating system, that memory address where you can go and find what you're looking for. Okay? If we always pass things by address, aren't we far, 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 far more memory efficient than if we always pass things by value? If we pass things by value, always, we're going to be passing houses around sometimes. But sometimes we're passing quarters around. Quarters, not a big deal. Maybe even makes sense. Houses, huge deal. Never makes sense. Well, the same is true in our programming languages. As programmers, we have to make that decision. Should something be sent a copy, passing it by value? Here is a copy of what I'm working with. So if I hand somebody a quarter, which looks exactly like this other quarter that I have in my pocket. So I take 2 quarters out, I hand you one, put the other one back in my pocket. I give you a copy of that quarter, right? And then you go home and you bend that quarter in half. When I go check my pocket later on, am I going to find a bent in half quarter in my pocket? No, because I gave you a copy of the quarter. You disfigured the copy, not the original, right? Okay? Now, if I give you the address of my house, and you go and flame my house up, when I come home, is my house going to be on fire? Yeah. Well, there's only one of those. You went to the real house. That wasn't like a toy house I gave you. It was the real deal. You went to the real place. Okay? That's the difference between value and address. Okay? Whenever something is passed by address, you are working with the real McCoy. You are dealing with the real object. Any changes you make are global changes. If you go to my house and knock out a window, that's a knocked out window. Anybody else comes to my house will see that knocked out window. If I give you a quarter and I have a quarter and you bend it in half, my quarter did not bend in half. Make sense? Okay, so the proof I made here with our integer array is that when I first created it out here in main and I printed out its memory address, it printed out this address right here. Then I passed it to this method called blah, right here. This guy took in an integer array as a parameter, and I printed it out there, and it printed out that. They are identical, correct? I passed that array by address. So any changes I make to that array inside of blah, I am changing those in the actual array. It's like you ran to my house and knocked out the window. We're working with the real array. So if I come in here, so back to our char array one, if I come into my char array and replace first element, and I change whatever's that bucket 0 to now be equal to C, that's a permanent change. Because you didn't hand me this little copy of the character array. You told me where to find it in memory. So I ran out to memory, went to bucket 0 and said, you are now this guy. And anybody else who has a pointer to that guy will now recognize the new version of that array. And we saw that right up here. Get rid of my int array thing here. So I created my char array, printed it out, HELLO. So there's my print. Then I called replace first element, passing it AR and J. Notice I am not receiving a return value here. I'm just passing it in, letting whatever happens, happens. And what does this guy do? He's one line. He just says change bucket 0 to whatever C was, which in this case was a J. And then it ended. This guy returned no value. Now I'm back in main. I print it again, and we see that that value was globally changed. So I should have hello, then I have jello. So when I passed AR and the J into replace first element, and it made that change was global because I'm able to still see it out here.
Wait, then which one made it unglobal again?
The string. We'll go back to string here in a second. Just want you to see that this is global. So arrays are passed by address or passed by reference, not by value. So when we pass an array to a method, any changes we make to that array are global changes. When we pass an int to a method, any changes we make to that int are local because ints are like quarters. When we pass an int to a method, we are passing that integer by value. We are giving that method a copy of the integer, not the integer itself, not a pointer to where that integer is in memory. Does that make sense? Now, this gets back to our conversation about strings, where strings are sometimes passed by, strings are definitely object types. Definitely object types. And all object types in Java are passed by address, except strings. all object types, I'll do a slide for this. So arrays are always passed by address. All objects are passed by address except strings. Strings are the one object, the one and only object that is treated like a primitive type. Primitive types are passed by value. Strings are passed by value. I'll put a little ish on that. The reason I'm throwing the ish on that is our perception is that strings are passed by value. That is, strings are passed and they are protected, so we cannot make global changes to them. The reality is they are passed by address so that we don't, if you have a 4,000 character string, you don't want to make a copy of that. That's almost as bad as a house, right? So strings are passed by address. But from our perspective, when we manipulate strings inside of a method, we are working with a protected copy of that memory. So any changes we make are local to just that method. They will not be global changes. So strings act as if they were passed by value, even though behind the scenes they are passed by address for memory efficiency reasons. Okay? But objects other than strings are always passed by address, which means is when we start talking about objects, if we pass an object into a method and we make changes to our object, those are global changes. That's true for every single object except strings. Why is that? Java, I've said it before, is a string-based language. Strings are very, 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 very important in Java. Therefore, Java has given us a special syntax for defining strings without using the new keyword. Call that syntactic sugar is how I usually refer to that. They've given us a nice syntax for creating strings. String s equals hello rather than the way we create every other object, which we'll see next week. They also allow us to work with strings as if they were primitive types, passing them to and from methods. Okay? So the evidence here is with my string example up here. I created a string named s, set it equal to hello. Printed out s, no surprise, it's going to print out hello, right? Then I passed it into replace first element, passing the string and passing j. Here's that version of replace first element. This guy comes in here. We set s, we take an s. Now remember, objects are passed by address. Strings are passed by address but are treated like they were passed by value. Okay? So what do I do in here? So this guy was passed by address. He's a string. He is an object, but he's also a string, so it's kind of an ish type situation. I promise you under the hood, he was passed by address. But he will be treated as if he was passed by value. And we'll see the evidence here. So we come in here, we create a brand new string called answer. We build answer up to be our correct thing. And then we try to overwrite s with answer, which should have given it a new value if it were passed by address, correct? This is saying set s's value, which is a memory address, equal to the memory address of answer, overwriting s. But when we came back out here and printed it out up here, and let me comment out these few things down here. So when we printed it out after that call, we'll see that it's still hello. That change was not global. That make sense? Proving that strings are passed as if they were passed by value. Arrays are passed by address. Questions about that? Okay. Now, arrays can be kind of helpful for us. For instance, we can use an array to store multiple pieces of information. So maybe we create a string array. We call this guy a record. This guy's going to be a new string array with 3 buckets in it. I'm going to say record at bucket 0 is equal to Mike. Record at bucket 1 is equal to Littman. Record at bucket 2 is equal to my cell phone number. So now I have a single variable called record that is actually holding 3 pieces of information that I could then use. So I could pass around this one variable record and use it to print out or use it to move around multiple pieces of information within a single variable name. Does that make sense? So right off the bat, arrays give us almost like a power tool that we did not have before. All right, now, why do we need this? Well, for right now, we need this because we don't have objects. So we put ourselves back in an older language like C. The C programming language being a procedural language. This is predating object-oriented languages, but not predating arrays. Arrays existed before object-oriented languages. In a language like C, being able to store more than one thing under a single variable name would be helpful. So creating an array and using it to store, in this case we're storing 3 pieces of information. In your homework assignment, which we'll talk about in a few minutes, you store 2 pieces of information. Being able to do that was very helpful, but the downside is what? The downside is we have to remember that bucket 0 holds the first name, and that bucket 1 holds the last name, and bucket 2 holds the phone number. We have to somehow document that somewhere. Does that make sense? So the upgrade to that was something called a struct, which we will talk about more next week. Struct was the gateway drug to object-oriented languages. So in a language like C, we had this thing called a struct, which is a structure. That's short for structure. And it allowed us to create a single variable type that would have 3 different parts, one being first name, last name, phone number, named like that. So we could say S dot first name, and it would give us that value. S dot last name, it would give us that value. S dot phone number, it would give us that value. We can't do that with arrays. Arrays, we have to remember what we put in each bucket. Okay? So we have the convenience of passing packaged up data around with a single variable name, but we do not have the convenience of knowing what we stored where, so we have to keep track of that. That make sense? Okay, so let's go. That's a little precursor type thing that you'll find helpful for your homework assignment. So let's go and write a couple of the methods that we wrote earlier for strings, but let's write them for arrays. So I'm going to create a method. Except this time we don't have to return the value. We're going to sort the method in line. So I'm going to say static void reorder array. This guy's going to take a char array, AR as a parameter. And I want this guy to go through and put AR in order. alphabetical, just like we did with hello. We got EHLLO. So if I create the character array, I'm going to show you a little shortcut for creating arrays. Char array AR, I'm going to set this guy equal to syntactic sugar. This is equivalent to char array AR equals new char array 5, and then AR bucket 0 equals H, AR bucket 1 equals E, blah, blah, blah. So nice shorthand for filling an array with some information that you already know. Okay, so I want this reorder array to take in a char array and put this array in alphabetical order. Now remember, we have the benefit of A, not having to return anything, assuming I want them to create a branch, assuming I want them to order it in line. If I want them to take the global array and just put it in alphabetical order, then we're set. If I don't want them to damage the original one, then I need to actually make a copy of it. Correct? To make a copy of it, I would need to create a brand new array. So like for instance, let's say we were going to write static char array make copy. And this guy took a char array as a parameter. This guy would create a new char array called copy is equal to a new char array of size ar.length. Then we'd say for its I is equal to 0, I is less than ar.length, I plus plus, copy at bucket I is equal to AR at bucket I. Return copy. So this little method here goes through and it duplicates an array for us. Make sense? Okay, so at the end of this, we still have our original AR, but we also have a brand new array that we called copy here. It'll have its own memory address that has all the contents of AR copied into it. But there are two physical arrays in that case. But in our case here, we want reorder array to take in a single array, in this case a char array, and we wanted to alphabetize it inline. So it has a global impact. We should globally change that array. How are we going to do that? Will our logic be different now that we change the way we're working? Now that we know that we can change around things within the array. What character do I want to have at bucket 0 of my array? Smallest character, right? I want to have the smallest character in there. How do I find the smallest character in an array? Pretty similarly to the way I found the smallest character in a string. Okay, so if I say for int I is equal to 0, I is less than ar.length, I plus plus. Somewhere I need to have a char cur winner, and maybe I start this guy off at AR at bucket 0. If I do that, maybe I start my loop off at position 1. So cur winner, AR at bucket 0. Loop starts off at 1, keeps going as long as I is less than AR.length, I plus plus. Now what do I want to do? Well, I'm essentially sorting this array. I need my smallest characters to bubble to the top. We have an algorithm called bubble sort. And this is how bubble sort would work. This is my original array. Looks like this. And I'll go ahead and list the buckets underneath it. We don't need to worry about memory addresses here. We just want to appreciate that they exist. Okay. And in the end, we'd like this to be EHLLO, alphabetized. The way bubble sort works is we start off, we need a couple of variables here. Maybe we call this guy cur. We start off looking at bucket 1. And we decide, should an E come before an H? So we start at bucket 1 because we are always comparing to the guy right before us. Should an E come before an H? It should. So we're going to swap those guys. In order to swap them, we're going to need an extra little storage place. So we're going to put the H into our storage container. Maybe this is called temp or something like that. Little char called temp. Then we'll overwrite that H with an E. Then we'll overwrite wherever cur is, which is an index, with the H. Then we follow. Now we're at the top of the list now, so we know that we're as far up as we can go. We've taken the E up as far as we can go right now. Okay? So now we need to reset. I need to remember where my previous start was. So even though cur followed it, I had to remember that previous start started there. So at the beginning, cur and previous start both point to the same place. Then cur followed the guy up to the beginning. What do we do then after we finish bubbling E all the way to the top? We increment previous start, make it one more than it used to be. I'm using pointers here like they're memory addresses, but these are just indexes. So originally, previous start was an integer that held 1. Cur was an index that held 1. So I'll increment previous start, then set cur back to whatever previous start is. Should an L come before an H? Nope. So we're done. No bubbling necessary. Increment previous start. Set cur start equal to previous start. And just for the sake of this argument, I'm going to put an A there at the very end, just so we do have another one that we have to hit. Okay? So, should an L come before an L? Nope, no swapping there. So what do? Previous start gets incremented. Cur points the same thing as previous start. Should an A come before an L? Yep. So we'll temporarily store the L, overwrite it with the A, then overwrite cur with the L. That's so we can preserve those values. And then cur follows. Should an A come before an L? Yep. Overwrite the L with an L. Overwrite the L with an A. Overwrite the A with an L. Cur follows. Should an A come before an H? Yep. Overwrite the L with an H. Overwrite the H with an A. Overwrite the A with an H. Cur follows. Should an A come before an E? Yep. Overwrite the H with an E. Overwrite the E with an A. Overwrite the A with whatever's in temp, which is an E. Cur follows. Is cur at the beginning of the list? Yes, it is. So we've bubbled the A up as far as we can go. Increment prev. Set cur to prev. Is prev pointing off the end of our list? It is. We're done. Is this guy now sorted? Yes. So we're going to go ahead and implement this for sorting our array. So what do we need? We need two variables, a prev start and a cur, and then we need a temp. Temp is a char that we use for swapping. We have char temp. We have an int prev start. We're going to start that guy off at 1. We have a int cur that we won't do anything with right now. All right, now we're going to need a loop. The loop is going to go through every element in there. Now, if we go back and look at this, would you agree that prev start went from bucket 1 to bucket 2 to bucket 3 to bucket 4 all the way off to the end? Prev start sounds like the counter in a loop, doesn't it? So could I actually do this? Create my temp, create my cur, write a for loop for int I, well, we'll call it prev start just so our stuff is stays the same as our little diagram. So for int prev start is equal to 1, prev start is less than ar dot length. Keep going until we hit the end of the array. Prev start plus plus. So prev start is going to go on a nice little voyage from bucket 1 to the end of our array. What do we do each time through? We set cur equal to whatever prev start currently is. Then we bubble characters up as long as we can. How do we tell? Well, when we were pointing here, when they were both pointing here at bucket 1, so this is like the first time through, we asked the question, should this character, that is the character at index cur, should this guy come before the character at index cur minus 1? We have to ask that question. So we'll say, if AR at bucket cur is less than AR at bucket cur minus 1. For right now, let's just assume everything's lowercase. Okay, we won't mess with upper and lowercase stuff right now just for the sake of learning this algorithm. Okay, so if AR at bucket cur is less than AR at cur minus 1, we need to do a swap. Right? We need to swap those two values. How are we going to swap the values? Well, we're going to set temp equal to AR at cur minus 1. Then we're going to set AR at cur minus 1 equal to AR at cur. Then we'll set AR at cur equal to temp. That make sense? How many times are we going to do this? We're going to do this until one of two things is true. Either we have bubbled all the way to the top of our list, that is, cur is equal to 0, or we should not do the swap. That makes sense? So we're going to keep doing this as long as cur is not equal to 0, and we should swap. As soon as one of those conditions is false, we're done, move on to the next prev. So we're actually going to put this inside of a while loop instead of an if. While we should swap, before we check to see if we should even swap, we're going to say cur is not equal to 0. And so while cur is not equal to 0, I'll put these even in parentheses just to clarify them a little bit. So while that's true and that's true, while both of those conditions are true, do the swap. Okay? Now, we talked about this probably the first class when we were talking about ands and ors. Java is smart. It will not do something stupid like if cur is currently 0, it won't check cur minus 1 because this is an and. As soon as it runs into one false, the whole thing is false with an and, right? That's why we specifically check to see if cur is not equal to 0 first. So as long as cur is not 0, and whatever's that cur should come before cur minus 1, do the swap. If cur is 0, we won't check. If cur is not 0, we know it's 1 or more, which means that we could look at cur minus 1. So we're going to keep doing this as long as we should swap or we hit the top of the list, hit the beginning of the array. As soon as we're done with this loop, we've bubbled something up as far as we can bubble it. We either weren't supposed to bubble it towards the front, or we bubbled it all the way to the front and we're done. So what do? We exit out of this while loop, spin back up, prev start gets to be 1 bigger than it used to be, and we set cur equal to the new prev start. And that's it. Go ahead.
So why do we even make cur and then put cur throughout that? If cur just keeps doing equal to prev start, why don't we just use prev start throughout the while loop?
Because we don't want to break prev start.
Oh.
Cur, notice in this, when cur was here, or let's say prev start was there, cur started pointing to the same place that prev start did. Then cur followed, but prev start stayed the same. Prev start reminds us where we need to go back to.
But since it's in a while loop, doesn't it make it like local or something?
No.
Oh.
Nope, the variables, all the variables in here are, this is a local, these are both local. This prev start is local only to this for loop. But cur was actually created higher up here.
Oh yeah, okay.
All right, so we wrote that code. We already have a print array available to us, so we're going to say driver.printArray AR. That'll print it out of order. Then we'll say driver.reorder. Well, I'll eventually call reorder, I think. Passing it AR. Then we'll say driver.printArray AR. And there's our sorted array using something called a bubble sort. And there's our reorder. So, first thing I'll tell you when you do things like this, always, always, always draw pictures. We're starting to get to the point now where our algorithms, while not difficult, will be confusing if you try to conceptualize them entirely in your head. This was a lot easier to write if we were able to follow a picture. If you tried to just write this off the top of your head, you're going to find that very difficult until you've done it 1,000 times. Okay?
You go, I don't know, somehow I'm missing something and it's not liking it. I don't know what I'm missing.
So I can look at it in a few minutes.
Okay.
So any other questions on this before I talk about your homework assignment? Okay, now bubble sort is something that is an industry standard. Okay, so this is something you would very likely use in industry. At some point, if it's not in 535, we'll talk about in the 537 class. We talk about some other ones called another one we call merge sort, which is a recursive algorithm. Very interesting, much shorter than this one, much more memory inefficient. But lends itself to multiple cores or multi-processing sorting. So super fast if you can dedicate 1,000 computers to sorting a terabyte of information. Not so fast, you have one core, you'll just run out of memory is what will happen actually. Okay, so in any case, here's our reorder array. The one thing we want to appreciate from this is notice how much shorter this total code is than the string equivalent of pulling off the same task. Also notice that we didn't have to build 10 strings and kill off 9 of them. Or 8 strings and kill off 9 strings and kill off 1 of them, whatever it was. Kill off 8 of them. We were pretty efficient. We worked all within the same memory footprint. We didn't kill off anything. We just moved things around inside the array. All right. So let's talk about your homework here for a few minutes. Well, by the way, it was brought to my attention that I did not post your grades for last week's assignment. I'll do that first thing tomorrow morning. Next time that happens, somebody text me or email me. I'm usually pretty good at staying up on grading, and I literally was watching golf for 10 hours on Saturday and Sunday, each of those days, sitting there grading. So I had plenty of time I could have graded. I just thought I was done. This was not a time constraint thing. I had nothing better to do during the commercial breaks than grade stuff. Let's see. We're homework 5 now, right? Okay. So, homework 5. Write a Java method that adds 2 fractions together and then returns the result in reduced form. So, for instance, 1/2 plus 1/4. Well, you're going to get a common denominator, right? So that's 4/8 plus 2/8, which is 6/8, or 3/4. Make sense? So you're doing fraction math, just addition. Now, so I understand, get the problem you're solving generalistically? All right. Now, a fraction should be represented as a 2-bucket integer array. So you would create an integer array, and in bucket 0, you'd put the numerator, and bucket 1, you'd put the denominator. So your method for adding fractions should take in 2 integer arrays, and then do all the necessary math. Make sense? Now, the punchline here is, you're not going to really recognize it on yours since you're just adding 2 fractions. But if you were adding thousands and thousands of fractions, this is kind of an interesting thing, you'll find that fractions represent a time complexity problem. Not fractions in and of themselves, but the reduction of fractions, reducing them to lowest common denominator. Lowest common terms. So your paper this week deals with that issue. Report number 5. Write a 3 to 5 page paper discussing algorithm design as it relates to time complexity problems, like reducing fractions without using the Euclidean algorithm for greatest common divisor. versus using the Euclidean algorithm for greatest common divisor. When initially solving a problem, how might one detect that a solution needs extra attention with respect to an efficient algorithm versus standard solutions, where a highly efficient solution may be indistinguishable from an inefficient one? Specifically discuss the potential trade-off between an easy-to-understand inefficient solution versus a difficult-to-follow efficient solution. Is it always better to write optimal code if the end result is difficult to follow by future programmers who may maintain your code? Make sense? Okay. You will not run into the issue in doing your homework where your program takes a while to run. I'll show you that next week. When you do your program, even if you write it inefficiently, it'll run fast because you're only adding 2 fractions. You can go and use the Euclidean algorithm if you want. You can find it and use it. But otherwise, I would encourage you in your first pass through this, when you're figuring out how to reduce fractions, try to do it on your own. Okay? Because the Euclidean algorithm won't make any sense to you in terms of how it's working. It just will work. All right? But what we'll talk about next time, and I'll actually do an example, is when you start adding up a lot of fractions and always reducing them, something that you expect should only take less than a second on a computer could literally take a day. Becomes a time complexity issue. So that's this week's theme. Okay? Questions, comments, concerns, bribes. We didn't get the 5 minutes early. It was because he was still out in the hall. He came back it's like 17, 18 minutes. All right. I'll see everybody next week, and I will have your stuff graded sometime tomorrow.